Hello and welcome to this video on a Neo4j GDS Link Prediction pipeline. So in this video, we will walk through the entire implementation of such a pipeline based on a publicly available dataset, the Citation Network, which we are going to use to implement this use case. So we will cover the data generation and import into Neo4j, and then we will walk through each of the steps of the pipeline, and I will give you some additional information about what's happening in each of the steps, so that we understand what we should keep in mind while creating such a pipeline, and also common pitfalls to avoid. In the end, I will also give some considerations about limitations of the current API of the pipeline, and we will end up with an entire working example during this video. So there's a lot to cover. Stay tuned. Leave a like if you like this video, and leave some questions in the comments. It helps me to understand what you're struggling with. And yeah, let's get started. Okay, so first of all, I want to show you the dataset I'm going to use, which is the Citation Network Dataset, which is publicly available. And if you download this file, I use this version 12 down here, you get a lot of papers and citations. And I will explain the data model in a second. But we will end up with a very large JSON file containing this data. It's about 17 gigabytes. So I did some pre-processing to filter this file to only contain some publications. It's been 3 that I've been using. And I stored this as a result. So a filtered JSON file, which we're going to load into Neo4j later. All right, let me show you how we can set up Neo4j to do this. So what I'm going to do is to start a very simple Docker container with Neo4j, and it has 2 plugins enabled as well, as it is configured here in this file. So that would be the APOC library and also the GDS, like the data science library of Neo4j. And I'm going to run this Docker container now. So that we have a Neo4j running instance. Okay, so while this is starting, I would like to show you the schema we are going to create in the next step. So if we load this data, it consists of articles and authors, and we are going to create a schema which looks like this. So articles have been written by authors and will be connected by a published edge. So each author which has contributed to an article will get such an edge. And also articles reference each other. So we will have references, edges between articles. And these articles will be published in venues. So the published in edge will show that an article has been published within a venue. And also the references in turn, they may have authors as well. So now that our Docker container is started, as you can see from here, we can go ahead and load the JSON file into our Neo4j. So, and therefore, we need to first create some constraints here so that we can merge articles, authors, and venues by ID. So we don't create them twice. So I will execute these 3 statements here, which basically will create these constraints for us. Once we've created them, we can load our JSON file into our Neo4j, and that one's done with this query here. So we basically run over each line in the JSON and create the structure that I have showed you previously. So if we execute this, it will create a couple of 100,000 nodes. And while it's running, while we're waiting, I will show you what we will do in the next step. So if we have the schema here on top, we can also consider that relationships between authors and articles with a published edge as a bipartite graph. So we could also depict it like this. So articles are always on the right and authors are always on the left. And the published edges, they connect the two. And we use this information, this structure, to create a so-called co-authorship graph. So what we want to have is, or we will end up with a homogeneous graph consisting only of authors and co-authored edges. And we will find this information by, for example, looking which other authors has author 1 collaborated previously. And therefore we would analyze this bipartite graph here. So we see that author 1 and author 2 have collaborated in 2 papers here on paper 1 and 2. And therefore we would create this co-authored edge with a property with a collaboration count on the edge, because they have 2 collaborations, and authors 2 and 3, they have collaborated only on paper 1, so they would have only 1 collaboration. So that's the co-authorship graph. It's a homogeneous graph consisting only of authors and co-authored edges, and is derived from the bipartite graph of authors and articles by analyzing the published edges. Okay, our insert query has finished in the meantime. So we have created in total 356,000 nodes, and we can explore them with our Neo4j browser now and see that we have created exactly the schema I've showed you before. So we can look at some authors here, and this author has authored 2 papers together with another author, and these actually have been published in the same venue. Oh yeah, exactly. And this one also has authored a 3rd paper, basically with some other authors. Now that's the schema, the base schema. And now we want to create our co-authorship graph. And therefore, we have another routine, which was open already, which is this one. So we would find such collaborations. So we find an author which has collaborated with another author, and then in the end would create the co-authored edges together with the count property on the edges, which is slightly different name than on the slide. But we can execute this query, and it's going to run for a while, and it's going to create our co-authorship graph. All right, so our query has finished, as we can see here in the very bottom line down there. It took 11 seconds, and it created 215,000 relationships in our graph. And we can have a look at them in our Neo4j browser. Maybe we have to, oh no, it's been there. Anyways, here are the co-authored edges. And we can see now how authors have actually collaborated here. All right, so on this homogeneous co-authorship graph, we want to do our link predictions. So we want to predict new co-authored edges to predict which authors may collaborate in the future. And therefore, I want to introduce you to the link prediction problem. So as I have depicted in this slide, so this is our homogeneous graph here on the left. And we want to predict if there should be an edge between node 1 and node 2. So basically what we're doing is we want to classify a pair of nodes, which is quite special for the link prediction task. So we take a pair of nodes, and then we want to classify, should there be a link or not a link? So we have 2 classes. Class 1 is, yes, there should be a link. Class 0 is no link. And therefore, we interpret this problem as a binary classification problem. Okay, secondly, I want to show you the basic steps which are required to create such a pipeline. And we will walk over them in detail for the rest of the video. And we will also do the implementation in the Neo4j GDS. Let's start with a short overview about what's going to happen within this pipeline. So we have our graph on the left here. We want to predict these edges, the red ones. We already discovered that it's going to be a binary classification problem we're going to solve. And we know that we're working on a pair of nodes. So as we've seen previously, one of the first steps is to add node properties, which is basically we take properties on each of the nodes and we tell the pipeline which properties it's supposed to use. So this would create a vector like this. X and 1 is the feature vector of node n1. So here we have added 3 properties. 2 of them are basically vectors and 1 of them is only scalar. And we do that. We add the same properties on all of the nodes in the graph. So after we have told the pipeline which properties to use for each of the nodes, we add a feature vector. And that's a very special step for link prediction tasks. And because we want to predict tuples of nodes, basically we want to predict links, or we want to classify node pairs, we have two vectors, which would be the input to our model. So therefore, we take the two nodes together with their feature vectors, and we need to combine them into a link vector. And the link vector is basically the feature vector, which is specific for one node pair. So it's the combination of both nodes. So what we do is we take the two feature vectors of each of the nodes and we combine them into a final link vector, which in turn will be the input to our model. So this feature vector X is specific to node N1 and O2. Both of them are combined. So on the Neo4j GDS pipeline, we currently have three combination functions, which are pretty straightforward. So one is L2, which would be the squared distance of the two vectors. Hadamard, which is the element-wise product. And cosine, which is the cosine similarity of the two vectors here. And we end up with a final vector or a scalar in the case of cosine similarity. And yeah, after we have combined both feature vectors, we have one vector for each of the node pairs. So that's the link feature vector step here. So after having our features ready, we can define data splits, which is a crucial step for link prediction. I'm going to explain later why. And here we want to split our input data into train, test, and feature sets, which would be three distinct sets, which is quite slightly different than from traditional machine learning tasks. And we will use the feature set only to calculate features that we have defined previously in the add node property step. So if we want to, for example, calculate some graph embeddings in the node features, the thing is that in a graph database, these algorithms, they use the structure in the neighborhood of the nodes to find the node embeddings. And the structure of the context of a node will be captured in this feature. So if we split our data into training and test set, but we calculate the features on the entire data set, the right solutions for our model training and testing are already captured by the algorithms generating the features for us. So here is a very common pitfall for link prediction tasks. So we split our data into three sets, and we use one set, the feature set, only for the feature calculation. And the three sets are distinct, so they don't contain any data point or actually an edge in common, so that we can be sure that our feature generation data is distinct from the training and test data. Okay, let's consider the co-authorship edges as our positive samples. So our positive samples are the edges that already exist in the graph, which we know are correct. Now we take this positive set with all the edges and split it into three sets, which would be the positive test set, the positive train set, and the positive feature input set. And the positive test set will be used for testing, the positive train set will be used for training, and the positive feature input set will be used for feature training. So we use only a subset of all edges in the graph to do the feature training. And we also use only a subset of the graph for training. And we also use a subset of the edges in the graph for testing. And they don't leak data between them. So we have positive samples in the graph, which are the currently existing edges, which we know are correct. And the negative samples, which we also need to train our model, are usually much more than the positive samples if we are not dealing with a almost or close to fully connected graph, because each node could potentially be connected to all of the other nodes. So which would give us a lot of negative samples in the graph. And therefore this set is much larger. So in order to circumvent a model which will always predict negative, like no edge in the graph, and yield high accuracy, we need to sample our negative samples so that we end up with as many positive as negative samples in each of the sets. So we sample our not existing edges to complement our positive samples. And we only do this for the test and training set, of course, because in the feature input set, we don't need negative examples, as the algorithms take into account the existing structure, which we have filtered. So they don't use negative samples. We only need them for training and testing. Okay, here's a slide to visualize how many negative samples we have for each of the nodes. So here we can see that node N1 could have in total 7 negative samples and only 2 positive samples. The 2 positive samples are the edges which exist to node N3 and N6. And the 7 is basically, it could link to all other nodes, which would be 9. And it has 2 links to 2 other nodes, so which would be 2. So we would end up with 7 negative samples for node N1. And if we consider the entire graph, we would have the combinations of all possible edges, which would be 9 times 10 divided by 2. And then we subtract 14 existing edges in the graph, which would be 31 negative samples in this small sample graph, while we only have 14 positive samples. And that's why we have an imbalance between positive and negative samples usually in such a use case. And therefore we sample the negative samples to have as many as we have positive samples in our graph as well. So finally, we will add model candidates to our pipeline. And in the Neo4j GDS library, there are currently 2 implementations for classifiers, which would be logistic regression and random forests. And we could potentially add both. And also we could add each of the models with different parameter spaces. And during the training of the model, the pipeline would actually evaluate each of these model candidates with a k-fold validation to find the best model with the best configuration. And in that final 2 steps for the model training and the predictions, we also need a projected subgraph containing the data which we want to be subject to training and predictions. The prediction step uses the stored winning model of the training step together with a prediction subgraph. So that subgraph could be potentially a different one that we wanna be subject for prediction. So the prediction step, we have 2 options. We could either stream the predicted relationships, or we could also write them back into the graph, and we could also set some parameters there about the threshold to use and so on. And yeah, we will see this during the implementation. All right, people, how did that go? It was quite some content, but basically we have understood what makes up a link prediction pipeline. And now we're going to look at the implementation of that. So it will become a little bit clearer as we look at the code, because the code tells us everything. All right, folks, here's the code. So what we start with is to create a graph prediction. So here we could actually specify either some node labels and relationship types together with an orientation, or we could even use some custom cipher queries to project a subgraph from our general graph. In this case, we create a graph projection called prediction graph. And that's going to contain only node labels author and relationships co-authored. And we specify the orientation here explicitly to be undirected, because the Neo4j link prediction pipeline, it works only on undirected edges. And then we also add the properties, which we have calculated in our preprocessing step. So we will end up with a graph prediction, and we can refer to it with its identifier here, prediction graph. Now we can start with our pipeline. So the create pipeline step is pretty straightforward. We only say create pipeline and give it a name. So we can go ahead and add node properties in our pipeline. And here we specify the pipeline name again and add a node property with the algorithm FastRP, which is a node embedding algorithm and basically projects node in our core authorship graph into an embedding space of 56 dimensions. So the node, the mutate property here is called embedding and will contain a 56 dimensional vector. And this vector is calculated such that nodes with a similar context in our graph will be mapped closely in the embedding space. That's what an embedding algorithm does. So we generate this feature right within the pipeline, which is a pretty important step because, as I said previously, only the pipeline has the knowledge about the feature input set. So this algorithm will be executed only on the feature input set. Okay, so we can go ahead and add this feature. So one step of the pipeline will be to calculate this feature on the feature input set. Secondly, we add another feature in this case. So we specify the pipeline again. We say, okay, we want to have a feature called degree, which is basically the node degree for each of the nodes. So this algorithm would also execute on a feature input set, this degree algorithm. And then finally, we also scale this degree feature to have a scale degree. So it's basically normalized over the entire data set. So all of these steps are for creating node features. And finally, to finish our features, we would combine, or we would say we want to add a link feature now. So for each node pair, remember the slide previously, we want to combine the individual features of the nodes into a link feature, a combined feature vector. And we do this twice. We could also do it in the same step, but to make this clear, we use the header mart combiner to combine the embedding features into a single vector, and also for the scale degree. So what we end up with for each node pair is a feature vector, a link feature vector, which consists of the embedding property of each of the nodes and the scale degree property of each of the nodes, and they are combined using the header mart combiner function. Finally, the data splitting step, it looks pretty straightforward. However, as I explained previously, it's a very important step for getting useful results out of your link prediction pipeline. And here I set the test and train fraction quite small because we need some data to train our features. So in this case, I set them to 0.1. So 10% of the positive samples in our graph will end up in the test fraction and 10% in the train fraction, and 80% will go into the feature input set. One second, what I said previously is actually wrong. So what we can see from the Neo4j documentation here, if we specify 10% is going to be the test fraction, means that we have 10% of our positive samples in the test set, and 90% of the data will go into the test complement set, and 10% of this test complement set, so basically 10% of 90%, will be in the train fraction, as it's saying here. So what's happening is that we take all positive examples, and the test set is going to be that fraction, test fraction, so 10%. And then it says down here, the train set is the train fraction of the test complement set. So basically of the remaining 90% of the entire data, we get 10% in the train fraction. That's a minor distinction, but yeah. Finally, we add one model candidate, which is going to be a logistic regression. So that would be our only model candidate. So we don't do too much optimization here. After we have understood how it works, we can iterate over that and test around with different parameters and so on. And then we are already heading to the interesting part. So here we can actually do some estimate of the training. But I would skip over to the next part, which is the actual training. So here we say, here we, for the first time, need our prediction graph, our graph projection, which we created in the very beginning. The rest is just the pipeline configuration. So didn't do anything. You already saw that these statements execute quite quickly. That's because we're only configuring how it's supposed to work. But here we, for the first time, input some data, our prediction graph. And what we do is we specify our pipeline, that one that we have configured previously, and we configure a final model name so that we can refer to it afterwards. And here we also have an important step, which is we configure the metrics that the model training should use to evaluate the model on the test data. Currently in the Neo4j GDS pipeline for a logistic regression, we only have one metric available, which is the area under curve precision recall metric, to evaluate our model and to find the best predicting model with its parameters. So if we execute this now, it will go ahead and obviously use the feature input set to calculate the features for each of the nodes. Combine the features for each node pair into a link vector and use this link vectors to train a model, a logistic regression with the train set, 10% of our positive samples, together with an equal amount of negative samples, and evaluate it against a test set, which is 10% of our positive samples with an equal amount of negative samples. And it will evaluate this model with the area under curve precision recall metric to find the best models, the best parameter and the winning model. And it will store the winning model under this name so we can use it later for predictions. So what we have is a winning model with an average train score of 0.94 and test score 0.94 and so on. So it's not so bad. However, we don't focus too much on this outcome here at the moment because we didn't do too much of model tuning here. This will be important if we start iterating over the features used or model parameters or model candidates for different ones. So then we can have a look. But out of the box, this looks quite promising. And finally, we can go ahead and use this trained model to actually calculate some predictions on our prediction graph. So we would use the same graph. And what this step would do is actually quite verbose because we want to predict links where there are no links in the graph. So all node pairs which are not connected, like all pairs of authors which are not connected by a co-authorship graph, will be evaluated by this model. And this leads to quite a large amount of combinations. I ran it before. I think it was something around a couple of 100 million combinations that this prediction step is evaluating. And then it would see, based on the trained model, whether there should exist an edge for this pair or not. And if you use the mutate option here, this step would actually write relationships back. It would create relationships in our graph projection, the prediction graph, and we can specify the name. And then we can also say, okay, only the top 40. So the 40 edges which the model is most certain about will be created. And we can also define a cutoff threshold. So everything which is classified below 0.45 with a probability of below 0.45 will not be created in our graph. After that, we end up with 80 new relationships, because this step will create directed relationships in both directions. So we always get 2 relations for one node pair. Once the step has finished, we can actually stream them back and write them back into our general graph. For now, after that step, they would all only exist in this prediction graph projection. So I can execute this here as well. And we see that it's starting to run at this moment. So that's it. So we have a pipeline. We can get some predictions. We have understood what the steps are. But as promised, I will give some considerations about common pitfalls. I will try to elaborate on them as well, and also limitations on the current pipeline as they exist now in the GDS. So the first limitation that I want to point out here is that it's not possible to add a feature for a node pair to our link vector. So as I explained previously, we can specify node features to use. So features on each of the nodes of a pair, which we then combine into a single vector, which will be the input to our model. So what's not possible is to have a feature for a node pair. So for example, if we had node 1 and node 2 and they have referenced the same paper, that would be a feature for the node pair rather than on each of the nodes individually. Features on a node individually would be, for example, node 1 has cited paper 1 and 2, and node 2 has cited paper 1 and 2. And we could do some one-hot encoding or anything like that. But it would also be nice to have a node feature, so like a node pair feature. So if we had node pair 1 and 2, we could have a direct feature, for example, cited same papers, and the value may be 2, which we could directly add to our X vector down here, the combined vector for the node pair, and we wouldn't have to use a combiner in that case. So this situation is depicted here. For example, we have authors here on the left and papers here on the right, and papers, they reference each other. So from analyzing this structure, we could go ahead and create new edges, basically, that these 2 authors have referenced the same paper. So author 1 and 2, they would have an overlapping set of 2 papers, which they have cited as well. And 1 and 3, they only would have 1. So paper 4 is cited by both papers of these 2 authors. And it would be nice to add this feature to our feature link vector. But as I said previously, at the moment, that's not possible. Also, what we need to take into account is that we probably would have to calculate our link features as well, only on the feature input set rather than also on the test and train set. And therefore, we would need to have fine-grained access to these sets within the pipeline. Or these features, which can be calculated by a custom query, need to be calculated right within the pipeline. The second limitation, which I want to point out here, is that we don't have any fine-grained access about how these sets here are generated. So, for example, if we wanted to have a custom splitting, so, for example, we wanted papers which have been published after 2015, for example, to end up in the test set, and everything previously to end up in the train set and in the feature input set. We are not able to do this at the moment with the GDS Link Prediction pipeline. Rather, it does a random sampling. And so I just wanted to point out that that's not possible. Also, we would need to have some fine-grained access to calculate these custom features, as I pointed out previously, because if we had some way to specify some markers which the pipeline is supposed to use to generate or to split our data into test and train sets. So, for example, we could mark our nodes or relationships as co-author test or co-author train, and tell the pipeline that these should go into train set, these should go into test set. we have more detailed access, and therefore we could also calculate custom features only on the feature input set. But at the moment, we don't have access to the splitting, and therefore we cannot have such a functionality. And then one final note on the negative sampling. So negative sampling is actually a research topic in itself. So there exist many approaches, and they also have influence on our model performance. I just wanted to mention that in this case, like in the Neo4j GDS pipelines, there's only one negative sampling strategy implemented at the moment, which is random sampling. So they would basically randomly choose negative samples from the graph and assign them to each of the sets. Oh man, that's been a thing, hey? But we made it. So what we've seen is how we can use a publicly available data set, the Citation Network Dataset, and pre-process it so that we can load it into Neo4j, create a homogeneous co-authorship graph from a bipartite graph of authors and papers, and use this homogeneous graph to implement a link prediction pipeline. We have looked at all of the steps of the link prediction pipeline and have explored some of the pitfalls. One of the major pitfalls is to generate graph features outside of the pipeline, because those graph features, they usually take into account graph structures and capture these structures into the features. And these features we would use for model training and testing and so on, and they actually capture the data we want to train. So what we do is we split our positive samples in the graph into 3 distinct sets, the test, train, and feature input set. And we use the feature input set only to calculate the features. And subsequently, we use the train set to train our model and the test set to test our model. But these sets, they are distinct so that we don't leak feature generation data into the test or train steps. Finally, we have seen how we combine node properties or node property vectors into a link vector, which is basically the feature vector for one node pair, which we in the end want to do a classification for. So therefore we use combiner functions of these node vectors, and we end up with a link vector, and that we use in our model training where we basically interpret our problem as a binary classification problem, whether there should be an edge or there shouldn't be an edge, and we yield quite good results there. And then we saw some limitations which we don't know whether the GDS team is working on to improve them or to fix them, or if we don't even know if it's on their agenda. But that's just what came across my mind when I did the research and tried to implement some things here. So we should be aware that we may have to build a custom solution once the Neo4j APIs don't suit our needs. So if you like this video, please leave me a like. If you have some questions, please leave them in the comments. I will also link a blog post which I wrote on this, so you can read everything on your own. And yeah, I'm happy to have you here, and I'm curious to hear what you say. I hope you enjoyed it, and see you next time. Until then, bye bye.